In this video lecture, we are going to be proving the sum to n terms formula for arithmetic sequences and geometric sequences. But before we continue, I want to firstly recap on what is an arithmetic sequence. So recall that an arithmetic sequence is a sequence which has a common difference between consecutive terms. Right, so what we're going to be doing today is we're going to be proving that the sum to n terms formula for an arithmetic sequence is given by n divided by 2 being multiplied into 2 times the first term in the sequence plus n minus 1 times d, where d is the common difference. So a is the first term and d is the common difference. Right, and our task today is to prove that this is certainly true. Now, when it comes to writing out a proof, I would like for you to understand that this is essentially a type of storytelling. It's storytelling which needs to include rigor and logic. And what we have to do is write down a sequence of logical statements such that when we are done, there is no doubt that Sn, the sum to n terms, is given by that formula. So that's what we are tasked with doing. Right, so firstly, what do we know? We have an arithmetic sequence, and we know that the general term in an arithmetic sequence is given by a plus n minus 1 times d, where a is the first term and d is the common difference. What do we want to prove? We want to write down a formula for the sum to n terms. We need to show that it is equal to that. But so far, all we know is that the sum to n terms is the sum of all of the terms from term 1 up to term n. So it's term 1 plus 2, term 2 plus term 3, adding all the way up to term n. Right, so I'll just include, for the sake of full understanding, the second last term in there. Now, the strategy we're going to employ is one that has been made famous by the mathematician Gauss. So I remember being taught this proof for the first time in grade 12 by my teacher, Mr. L. Pillay from Greenbury Secondary. And back then he told me a story that Gauss had derived this formula when he was in primary school after he was given this question by his teacher as a punishment. Right, so what strategy did Gauss then use? Gauss decided to write down and express the sum to n terms in two ways. So the first of which is what I've written down. So he wrote it by writing down the sum in the following order, going in ascending order from T1 up to Tn. So let's further unpack T1 to Tn. We know that term 1 is A, right? So what is term 2? Remember, there's a common difference, so it should be A plus D. So it's term 1 plus the common difference, D. Term 3 will then be your second term plus the common difference, D again. So it's A plus D plus another D, which is 2D. Or alternatively, instead of following that logic, since we have the general term formula, you could simply ascertain that T3 is going to equal to A plus 3 minus 1 times D, which is A plus 2D. And you will be able to generate T4, T5, 6, and so on, depending on how many terms we have in here. Right, so Tn minus 1 by our general formula is A plus n minus 2 times d. And of course we know that Tn is given by A plus n minus 1 d. Right, so what I'm going to do is I'm going to label this last equation, this sum to n terms, here as equation 1. Right, so that's the first equation that Gauss wrote down. And thereafter, Gauss decided to express the sum to n terms in a different way. So he then decided to write down the sum to n terms instead of in ascending order of the terms, now in descending order. So in the following way, Tn plus tn minus 1, continuing all the way back down to t1. So you're still summing all of the terms, but you've changed the order in writing the terms in the sum. So t3 plus t2 plus t1. And of course, let's just write down what each of these terms mean. So we then have that tn, of course, by our general formula, is a plus n minus 1 times d. We have that tn minus 1 is a plus n minus 2 times d. We could then write the third term in there. And continuing in the sum, I'll write down the second last term, t2, which is a plus d. And I'll write down our last term, t1, which is a. So that is what we have. So once Gauss wrote down the sum to n terms in two different ways, so we'll now label the second way equation 2, he then added them together. So we're going to find out, we're going to compute equation 1 plus equation 2. That's what we want. So we're going to add that equation to this one. So remember, when you're adding, you're going to add corresponding terms. You add everything on the left of the equality, and you will add everything on the right of the equality. So what terms do we have on the left of equation 1? We have Sn. What term do we have on the left of the equality in equation 2? We also have Sn. So we have Sn plus Sn, which is 2 times Sn. And now let's write down the sums that we have on the right-hand side. So when we're looking at the right-hand side, we are going to add corresponding terms. So we are now going to add the first term in here with the first term on the right-hand side. So it's a plus n minus 1 times d, which is actually 2a plus n minus 1 times d. So that's what I obtain when I add the first terms from each equation, and I'm taking the first term from the right hand side. We then add the second terms, so a plus d being added to this square bracket. And observe, when we add a plus d to this square bracket, we once again get 2a plus n minus 1 times d. You then repeat the procedure. Take the third term from the right-hand side of equation 1 and you add it to the third term from the right-hand side of equation 2, continuing up to the nth term on the right-hand side. So before we get to the last term on the right-hand side of each of these equations, let's add the second last terms. So I'm going to add the second last term, which is a plus n minus 2 times d, being added to the second last term on the right-hand side of equation 2, being added to a plus d. And once again, observe that I get 2 times a plus n minus 1 times d. When I add the last term in here to the last term in here, then once again I get 2a plus n minus 1 times d. So in this process of adding corresponding terms from the right-hand side of each of these equations together, observe that every time we added them, we got back the same term, 2a plus n minus 1 times d. So in order to sum up everything, it would be good to do the following. We would need to count the number of terms that we are adding in here. So how many identical terms do we have written on the right-hand side? Observe that we have n of them because we added n terms to n terms to write this down. So we have n terms written down here. So if I have n terms, n identical terms being added to each other, then essentially what this means is that I have n times 2 times a being added to n minus 1 times d on the right hand side, and 2 times Sn is equal to that. So that means that Sn is then equal to whatever's on the right hand side divided by 2. So that means it's n over 2 distributed into 2 times a plus n minus 1 times d. And this is precisely the sum to n terms formula which we were required to obtain. Right, so of course this was the strategy that Gauss had made famous. Right, so that is dealing with the sum to n terms for arithmetic sequences. Let's now discuss the sum to n terms for geometric sequences. Alright, so suppose we have a geometric sequence with first term a and common ratio r. Right, so if we ensure that r is not equal to 1, then we can show that the sum to n terms is equal to a distributed into r to the n minus 1 divided by r minus 1 when r is greater than 1. Or we can obtain the formula given by the following when r is less than 1. Observe that it was necessary to ensure that r is not equal to 1, for if it is equal to 1, then the denominator in each of these expressions will be 0, and division by 0 is undefined. Alright, so once again, let's write down a logical story that proves without a doubt that this is indeed the sum to n terms formula for a geometric sequence. So we will be proving the first formula. Right, so firstly we need to make sure that r does not equal to 1. Right. So what we're going to do now, as we had done before, is to write down the sum to n terms. What does it represent? Right, so it's term 1 plus term 2 all the way up to and including term n. That is what we have it to be. Of course, remember, we do have, since this is a geometric sequence, we know that for a geometric sequence, the nth term is equal to a times r raised to the power n minus 1. So it's important to take a note of that. Right, so now let's write down what each term in this sum actually is in terms of our general formula. So we know that T1 is a, because our first term in the sequence is a. T2 will then be the first term multiplied to the common ratio, so it's a times r. Right, if we wanted, we could also write down T3. That will be your second term multiplied to the common ratio r, so it's a times r squared. Or of course, if we didn't want to do that, we could use our general formula. So that means T3 will then equal to a times r raised to the power 3 minus 1, which means it is a times r squared. Right, and then continuing in that fashion, the nth minus first term will then be a times r raised to the power n minus 2, if you use that formula. And of course, we know that Tn is a times r raised to the power n minus 1. Right. So we now have that the sum to n terms can be expressed as follows. So once again, let's label this equation. So I'm going to label this equation, equation 1. Alright, so now what I'm going to do is I'm now going to multiply this equation by r. So I want to obtain r times Sn. So multiply every term on the right hand side by r. I then obtain a times r plus a times r squared plus a times r cubed. So multiplying everything by r, this becomes a times r to the n minus 1, because when you multiply by r, you'll be adding 1 into the exponent. And the last term becomes a times r raised to the power n. Again, by adding 1 to the exponent, I then obtain an exponent of n. So r times Sn equals to the following. And I'm now going to label that equation, equation 2. Right, now what we're going to be computing is we're now going to take equation 2 minus equation 1. That's what we're going to take. So by taking equation 2 minus equation 1, we have r times Sn minus whatever was on the left hand side of the equality, which is Sn. And this must then be equal to the same difference on the right hand side. Now we need to focus on the terms on the right hand side of the equality. Right, so if we're taking this and we're subtracting away those terms, let's find out if there are any common terms. Observe we have AR and AR. So when equation 2 subtracts equation 1 from it, these terms will cancel. I then have AR and AR squared. So once again, that's going to cancel. And notice that all terms from AR up to up to A times R to the n minus 1 will then cancel. So everything from this point to that point cancels because we are subtracting those terms away from it. So that then cancels with that. And the term before this would have cancelled with that. So what are we left with when we are performing the subtraction? If you look at equation 2, the only thing that's left on the right hand side is the term A times R raised to the power n. And what are we subtracting? What's left behind in equation 1? We are then subtracting. The only term left behind is A, so we're minusing A. Right, so this is what we have when we take equation 2 minus equation 1. So looking at this statement, on the left hand side, remember the end point here is that we want to solve for Sn. So let's factor out Sn. When I factor out Sn from here, I'm left with R minus 1. Looking at the right hand side, I observe that A is common. So I'm going to factor A out. When I do that, I then observe that R to the n minus 1 is left over. And now solving for Sn, I see that Sn is equal to A into R to the n minus 1 divided by R minus 1. And this is indeed the formula that we had obtained, that is stated for the case when R is greater than 1. Now notice, when we did the division, this division was allowed. We had to divide both sides by R minus 1. And this was allowed precisely because R does not equal to 1. If R was allowed to be equal to 1, then this division would not be possible. Right, so this is the case. So we have now proven the formula for when R is greater than 1. Similarly, by computing the following, instead of taking equation 2 and subtracting equation 1, if we did the reverse, if we said equation 1 minus equation 2, so by computing Sn minus R times Sn, we can then obtain the formula Sn equals to A distributed into 1 minus R to the n divided by 1 minus R, which is the formula for the case when R is less than 1. So that is how we prove without a doubt that each of these formulas are indeed true. Right, so before I end, I just want to discuss what happens in the case when R does equal to 1. Why do we not have a formula for it? And maybe we do. Right, so if R equals to 1, right, so that's the end of the proof. Right, so the proof ends there. Right, so now just some remarks. If R equals to 1, what does this mean? This means that the common ratio is 1. Right, so if R is 1, then the sequence is given by your first term, and which is A, and then the second term is determined by your first term times the common ratio R. So that becomes A times 1, which is again A. And then your third term will be determined by your second term times R, but once again that's A times 1, so it's A. Similarly, we can repeat the procedure. The fourth term is the third term times R, which would be A. So that means in any sequence where R equals to 1 is your common ratio, then that sequence is simply the list of the first term constantly. So it's a constant term for each Tn, so meaning that Tn equals to A for all n. That's precisely what it is. Example, maybe I had a sequence with terms 3, 3, 3 continuing indefinitely. So this would then be, this is a geometric sequence with r equals to 1. That's precisely what we have in here. And then what would be the sum to n terms? Then the sum to n terms will then be that constant number which is your first term, and since I'm adding it, I want to find out what is the first n terms being added together, and I'm adding it n times. It means that it will then be n times a. So in the above sequence, where the constant value is 3 for each term, the sum to, for example, the first 5 terms will then be 5 times 3, right, where the sequence is the following. Right, and that's where I'm going to end this video lecture.